Heat exchangers are essential components in countless industrial processes. They facilitate efficient heat transfer between fluids, enabling critical operations like heating, cooling, and condensation. From power generation and chemical processing to HVAC systems and refrigeration, heat exchangers play a vital role in ensuring optimal temperature control and energy efficiency. Their importance in modern industry cannot be overstated, as they directly impact product quality, process efficiency, and overall operational costs. Efficient heat transfer is paramount in achieving desired temperature targets and minimizing energy losses. Heat exchangers are meticulously designed to maximize heat transfer rates while minimizing pressure drops and ensuring structural integrity under various operating conditions. The performance of a heat exchanger is influenced by factors such as its geometry, flow arrangement, fluid properties, and operating parameters. Optimizing these factors is crucial for achieving maximum efficiency and minimizing energy consumption. The design and optimization of heat exchangers have traditionally relied on empirical correlations and experimental testing. While these methods provide valuable insights, they can be time-consuming, expensive, and limited in their ability to capture the complex flow and heat transfer phenomena occurring within these devices. Computational Fluid Dynamics, or CFD, has emerged as a powerful tool for overcoming these limitations, offering detailed insights into the intricate workings of heat exchangers and enabling engineers to optimize their designs for superior performance. Computational Fluid Dynamics, often referred to as CFD, is a sophisticated numerical technique used to simulate fluid flow, heat transfer, and other related phenomena. It involves solving complex mathematical equations that govern fluid behavior within a defined domain, providing detailed information about velocity, pressure, temperature, and other relevant parameters. CFD simulations offer a virtual testing ground for engineers, allowing them to visualize and analyze fluid flow patterns, temperature distributions, and heat transfer characteristics within heat exchangers. By leveraging the power of CFD, engineers can gain deep insights into the performance of heat exchangers under various operating conditions. They can identify areas of high pressure drop, flow recirculation, or inadequate heat transfer, which can hinder efficiency and compromise performance. This information is invaluable for optimizing heat exchanger designs, enabling engineers to make informed decisions regarding geometry modifications, flow arrangement adjustments, and material selection. CFD simulations offer several advantages over traditional experimental methods. They are cost-effective, as they eliminate the need for expensive prototypes and physical testing facilities. They provide faster turnaround times, allowing engineers to explore multiple design iterations in a shorter period. Moreover, CFD simulations offer a high level of detail and accuracy, capturing the complex flow and heat transfer phenomena that are difficult to observe experimentally. CFD offers a range of modeling approaches to simulate heat exchangers, each with its own strengths and limitations. Selecting the appropriate approach depends on the specific application, the level of detail required, and the available computational resources. The Radiator Model is a simplified approach that treats the heat exchanger as a heat source or sink within the flow domain. It's computationally efficient but provides limited information about the internal flow and heat transfer characteristics. The Porous Media Energy Source method models the heat exchanger as a porous medium with an assigned heat source or sink. It captures some aspects of the internal flow resistance and heat transfer, but may not be suitable for complex geometries. Macro models use simplified representations of the heat exchanger's internal structure, such as equivalent flow resistances and heat transfer coefficients. They offer a good balance between accuracy and computational cost, making them suitable for many applications. Dual cell-based models are an advanced approach that uses separate computational cells for the hot and cold fluids, separated by a wall with defined thermal properties. This method provides the highest level of detail and accuracy, but is computationally demanding. Each modeling approach has its own set of assumptions and limitations. Engineers must carefully consider the specific requirements of their simulation and choose the approach that best balances accuracy, computational cost, and the desired level of detail. ANSYS Fluent is a leading CFD software package widely used for simulating fluid flow and heat transfer in various applications, including heat exchangers. Fluent 14.5 offers a comprehensive suite of tools and features specifically designed for heat exchanger analysis, making it a powerful tool for engineers seeking to optimize the performance of these critical devices. One of the key features of Fluent 14.5 is its extensive library of macro heat exchanger models. These models provide simplified representations of complex heat exchanger geometries, allowing engineers to simulate their performance with reasonable accuracy and computational efficiency. Fluent's macro models cover a wide range of heat exchanger types, including shell and tube, plate, and compact heat exchangers. In addition to its macro model library, Fluent 14.5 offers advanced capabilities for modeling conjugate heat transfer, which involves the simultaneous simulation of heat transfer in both the solid and fluid domains. This is particularly important for heat exchangers, where heat transfer through the walls separating the hot and cold fluids plays a significant role in overall performance. Fluent 14.5 also provides robust tools for mesh generation, which is the process of dividing the computational domain into smaller elements or cells. A high-quality mesh is essential for accurate CFD simulations. Fluent offers various meshing options, including structured, unstructured, and hybrid meshes, allowing engineers to choose the most appropriate approach for their specific geometry and simulation requirements. Mesh generation is a critical step in any CFD simulation, as the quality of the mesh directly impacts the accuracy and reliability of the results. ANSYS Fluent provides a comprehensive set of tools for generating high-quality meshes that accurately represent the geometry of the heat exchanger and capture the relevant flow features. Fluent offers various meshing approaches, including structured, unstructured, and hybrid meshing techniques. Structured meshes consist of regularly arranged cells, typically quadrilaterals in 2 dimensions, and hexahedra in 3 dimensions. They offer high accuracy and computational efficiency for simple geometries, but can be challenging to generate for complex shapes. Unstructured meshes employ irregularly shaped cells, such as triangles in 2 dimensions, and tetrahedra in 3 dimensions. They offer greater flexibility in representing complex geometries, but may require more computational resources. Hybrid meshes combine elements of structured and unstructured meshes, leveraging the strengths of each approach to provide an optimal balance between accuracy, computational cost, and geometric flexibility. Once the CFD simulation is complete, ANSYS Fluent provides powerful post-processing tools for visualizing and analyzing the results. Engineers can generate contour plots, vector plots, and animations to visualize flow patterns, temperature distributions, and pressure variations within the heat exchanger. Fluent also allows for the extraction of quantitative data, such as pressure drops, heat transfer rates, and flow velocities, at specific locations or across defined surfaces. MR-CFD is a leading provider of advanced engineering simulation services, specializing in computational fluid dynamics analysis for a wide range of industries. With a team of experienced CFD engineers and a deep understanding of heat transfer phenomena, MR-CFD offers comprehensive solutions for heat exchanger design, optimization, and troubleshooting. Their expertise covers various heat exchanger types, including shell and tube, plate, compact, and microchannel heat exchangers. MR-CFD leverages state-of-the-art CFD software, including ANSYS Fluent, to deliver accurate and reliable simulation results. They employ a rigorous simulation process that begins with a thorough understanding of the client's requirements, followed by detailed geometry modeling, mesh generation, simulation setup, and post-processing analysis. MR-CFD's team works closely with clients throughout the entire simulation process, providing regular updates and clear explanations of the results. MR-CFD's services extend beyond simply providing simulation results. Their engineers possess a deep understanding of heat exchanger design principles and can provide valuable insights and recommendations for optimizing performance, reducing pressure drop, and minimizing fouling. They work closely with clients to develop innovative solutions that meet their specific needs and challenges. MR-CFD's advanced CFD modeling techniques empower engineers to optimize heat exchanger designs for enhanced efficiency and reduced costs. By accurately simulating fluid flow and heat transfer within these devices, MR-CFD helps identify design flaws, optimize flow paths, and improve heat transfer rates, leading to significant performance improvements and cost savings. Reduced pressure drop. MR-CFD's simulations can identify areas of high pressure drop within heat exchangers, allowing engineers to optimize flow paths, reduce turbulence, and minimize energy losses. This translates into reduced pumping costs and improved overall system efficiency. Enhanced heat transfer. By analyzing temperature distributions and heat transfer coefficients, MR-CFD helps engineers identify areas of low heat transfer efficiency. This information guides the optimization of heat exchanger geometry, flow arrangements, and material selection to maximize heat transfer rates and improve thermal performance. Minimized fouling. Fouling, the accumulation of unwanted deposits on heat transfer surfaces, can significantly reduce heat exchanger efficiency over time. MR-CFD's simulations can predict fouling patterns and rates, enabling engineers to implement design modifications or cleaning schedules that minimize fouling and maintain optimal performance. By leveraging MR-CFD's expertise in heat exchanger CFD simulation, companies can achieve significant cost savings through reduced energy consumption, extended equipment lifespan, and minimized maintenance requirements. The insights gained from these simulations enable data-driven design decisions that optimize heat exchanger performance and contribute to a more sustainable and cost-effective operation. Tailoring CFD solutions for optimal heat exchanger performance. Choosing the right CFD modeling approach is crucial for obtaining accurate and meaningful results. The complexity of the heat exchanger geometry, the desired level of detail, and the available computational resources all factor into this decision. MR-CFD's experienced engineers work closely with clients to understand their specific needs and recommend the most appropriate modeling approach for their heat exchanger simulation. For simple heat exchanger geometries, or when computational resources are limited, simplified approaches like the Radiator Model or Porous Media Models may suffice. These methods provide a quick and cost-effective way to gain insights into overall heat transfer characteristics and pressure drop. However, they may not capture the intricate flow details within the heat exchanger. When higher accuracy and detailed flow information are required, more sophisticated approaches like macro models or dual cell-based models are employed. Macro models offer a good balance between accuracy and computational cost, making them suitable for many industrial applications. Dual cell-based models provide the highest level of detail, capturing the complex interactions between the hot and cold fluids, but require more computational resources. MR-CFD's expertise in various CFD modeling approaches ensures that clients receive the most appropriate and cost-effective solution for their specific heat exchanger simulation needs. Their engineers carefully consider the trade-offs between accuracy, computational cost, and the desired level of detail to deliver simulations that provide meaningful insights and drive optimal design decisions. Case studies. MR-CFD's success stories in heat exchanger optimization. MR-CFD has a proven track record of delivering successful heat exchanger optimization solutions across various industries. Their case studies demonstrate the tangible benefits of leveraging CFD simulations to improve heat exchanger performance, reduce costs, and enhance overall system efficiency. Case Study 1. Shell and Tube Heat Exchanger. Optimization for a chemical processing plant. MR-CFD was tasked with optimizing the design of a shell and tube heat exchanger used in a chemical processing plant. Using CFD simulations, they identified areas of high pressure drop and low heat transfer efficiency. By modifying the baffle arrangement and tube layout, they significantly reduced pressure drop and increased heat transfer rate, resulting in substantial energy savings and improved process efficiency for the client. Case Study 2-Plate Heat Exchanger, designed for a food and beverage company. A food and beverage company approached MR-CFD to design a new plate heat exchanger for a specific product line. MR-CFD used CFD simulations to optimize the plate geometry, channel spacing, and flow arrangement to achieve the desired heat transfer rate within the specified pressure drop limits. The optimized plate heat exchanger design resulted in reduced energy consumption and improved product quality for the client. These case studies highlight MR-CFD's capability to address diverse heat exchanger design challenges across various industries. Their expertise in CFD modeling, coupled with their deep understanding of heat transfer principles, enables them to deliver tailored solutions that optimize heat exchanger performance, reduce costs, and improve overall system efficiency for their clients. The future of heat exchanger design, embracing innovation with CFD. As industries strive for increased efficiency, reduced environmental impact, and enhanced sustainability, the demand for high-performance heat exchangers continues to grow. CFD simulations are playing an increasingly crucial role in meeting this demand, enabling the development of innovative heat exchanger designs that push the boundaries of thermal performance. Advancements in CFD software and hardware, coupled with the increasing availability of high-performance computing resources, are driving the development of more sophisticated and accurate heat exchanger simulations. These simulations can capture complex phenomena such as multiphase flow, phase change, and chemical reactions, providing unprecedented insights into the intricate workings of these devices. The future of heat exchanger design lies in embracing these advancements and leveraging the power of CFD to drive innovation. By integrating CFD simulations into the early stages of the design process, engineers can explore a wider range of design options, optimize performance for specific operating conditions, and reduce the reliance on costly and time-consuming physical prototypes. Conclusion: the power of CFD and expert collaboration. Heat exchangers are essential components in countless industrial processes, and their efficient operation is crucial for minimizing energy consumption, reducing costs, and ensuring environmental sustainability. Computational Fluid Dynamics, or CFD, has emerged as a powerful tool for understanding, optimizing, and innovating heat exchanger designs. ANSYS Fluent 14.5 provides a comprehensive suite of tools for simulating fluid flow and heat transfer in heat exchangers, offering various modeling approaches to suit different application requirements. From simplified radiator models to highly detailed dual cell-based models, Fluent empowers engineers to choose the most appropriate approach for their specific needs. MR-CFD's expertise in heat exchanger CFD simulations provides invaluable support to companies seeking to optimize their designs for enhanced performance and reduced costs. Their team of experienced CFD engineers leverages state-of-the-art software like ANSYS Fluent to deliver accurate and reliable simulation results, guiding data-driven design decisions that lead to improved heat transfer efficiency, reduced pressure drop, and minimized fouling. By embracing the power of CFD and collaborating with expert simulation partners like MR-CFD, companies can unlock the full potential of their heat exchanger designs, achieving significant cost savings, enhancing system efficiency, and contributing to a more sustainable future.